Significant progress in the study of lightning has only really been made over the past 10 years. We now know that when a storm is overhead, the negative charge held within the base of the cloud creates a gigantic electrical field between the cloud and the ground. Weak electrical discharges can then jump downwards to Earth, gaining in intensity as they do so. This initial reaction is known as the downward stepped leader. As this leader gets closer to the ground, it increases the intensity of the electrical field and induces ionization at the tip of any prominent object. This ionization, in turn, develops to create a second phenomenon prior to the lightning flash, known as the upward leader. When these two discharges meet, the circuit is completed, allowing the current to flow. The characteristic bright flash of light and its accompanying roll of thunder. The electrical discharge, which may appear to happen only once, can in fact be followed by a dozen successive return strokes, each one lasting no longer than a few milliseconds. What exactly is the function of Benjamin Franklin's lightning conductor? Because it's connected to the ground, the single rod has a naturally occurring electrical activity. This is what's known as the corona effect. This means that conditions around the rod are ideal to set off the upward leader and create a preferential path for the lightning strike. The electrical discharge is then channeled safely away through the earthing system. Obviously, the quicker the lightning conductor builds up an upward leader, the more likely it is to meet the downward leader and thereby create this preferential path. With over 40 years' experience in lightning research, Indelec has developed a new generation of autonomous early streamer emission lightning conductors, the Prevectron 2. Here's how it works. Let's take a metal tip connected permanently to Earth so that the current may flow down it. In this way, we already have a single rod lightning conductor. We add an ionizing device to the tip, protected with a stainless steel housing, and connect this to a lower series of sensors to collect any ambient electrical energy. Then we add an upper series of spark-generating electrodes to obtain a very effective lightning conductor, which will now produce ions when a storm approaches, thereby initiating an upward leader more quickly. The attractive capacity of the Prevectron is thereby increased, as is the protection radius. During its development process, the Prevectron was constantly subjected to quality tests by major European laboratories. The experiment being prepared is designed to compare the performance of a Prevectron in comparison with a single rod conductor. This set of experiments is designed to compare the triggering times. The results are conclusive. When compared to a traditional rod, the triggering times of the Prevectron are considerably lower, up to 60 microseconds for the top-of-the-range model. Depending on the gain in triggering time, the French national standard NFC 17102 will allow each model to be assigned its own protection radius value. Lab tests can't tell the whole story, of course. For instance, naturally occurring lightning produces a much more complex and more powerful arc. We've now come to Camp Blanding in Florida, a region where storm conditions are a common-day occurrence. Indelec and the French Atomic Energy Commission have been conducting regular experiments in real-life storm conditions for a number of years. The site is particularly useful as it is possible to trigger a lightning strike almost at will. When atmospheric conditions are just right, the rocket is fired up towards the cloud at a speed of 250 meters per second, carrying up behind it the 700 meters of copper and Kevlar wire. The first few dozen meters of the wire are non-conducting, so as to allow the discharge to choose its own route down to Earth. When the rocket goes into the cloud, a short circuit occurs to the ground. The moment is right and the rocket is fired. Similar tests were carried out in France. Several recent Provectron models are put to the test on this launch pad. A nighttime discharge enables the extraordinary effectiveness of the Provectron to be demonstrated. If we play back the action in slow motion, we can see the rocket being fired up towards the storm cloud, making the connection with the ground. An electrical current then flows down the conductive wire, causing it to vaporize. A secondary phase shows the nearby Provectron reacting to the electrical field by generating an upward leader, which connects up with the conductive channel generated just before. An initial return stroke is then set off, followed by a second. Real-life experiments like these represent an invaluable source of research information and allow Indelec's engineers to offer ever more efficient lightning protection.